geomorphologist and co-owner of Pacific Watershed Associates in Arcata. He's got over 30 years experience working in applied geomorphology, erosion, and sedimentation studies. He's concentrated on water quality protection, erosion and sediment control, and fisheries restoration achieved through watershed rehabilitation and sediment control activities in steep land drainage basins. I've had the pleasure of working with Bill for over 10 years, and I have to say that capturing this knowledge that he has in the last presentation and in this one, I think is ultimately going to be a good service to the road management community. So thank you, Bill, and you're on.
All right, thanks, Richard. I guess, in response to the poll, it points out, I think, one of the main difficulties with monitoring watershed restoration, let alone road restoration. It could be riparian restoration, could be land management practices. It's really difficult, and it's typically pretty expensive. And that's why people back themselves up till they get to the site scale, where they can monitor a specific slope or a specific channel that they're doing restoration work in and actually see the results of their activities. And that's the most easily done, the most kind of efficient and cost-effective methodology. But it kind of begs the question and leaves the question open to, are you really doing for downstream areas what you anticipate or your objective is, improving aquatic habitat, improving water quality, and protecting or restoring fisheries resources. So I had two choices to go in this presentation today, and that was one, looked at the details of how you conduct site scale and reach scale in terms of streams monitoring to pick up the impacts and results or benefits of restoration work. And I think that's pretty well described in the literature, so I didn't go that route. Instead, I stepped back from a little bit to talk a little bit about monitoring, what it means in terms of road upgrading and decommissioning, how last week's presentation about the different tasks that you do in road upgrading and road decommissioning with the aim of protecting habitat and water quality, how those different tasks can be monitored, and then to look at some of the obstacles, and then ending up with a case study that we did on doing a monitoring, or kind of a retrospective monitoring and evaluation of road decommissioning projects that have been conducted under the Department of Fish and Game's Restoration Grant Program for the first, 6 or 8 years. So if you remember from last week, we had a 7-step process described for inventorying and treating road erosion. Well, I really wanted to point to the bottom 2, which is really once you've implemented the upgrading and decommissioning projects, then implementing effectiveness, conducting implementation monitoring and effectiveness monitoring and what those mean, and then maintenance of the project and what kind of maintenance monitoring would be appropriate for that kind of setting. So let's step back a little bit and take a look at monitoring in the context of road upgrading and decommissioning. And there's going to be a lot of words on a number of the slides, and bear with me, but I think there's some important concepts to relate. There's a lot of literature out there on monitoring, both at the federal level and at the state level, and some at the private level in terms of publications, but a lot of it's being done by regulatory agencies or land management agencies. There's really 4 types of monitoring that I want to discuss. One is the pre-project monitoring or documentation of conditions as they exist prior to your project. It's kind of baseline monitoring, determining what sediment production and delivery rates currently are or are likely to be, developing a sediment budget for your particular little sub-watershed or your particular project area that tells you how much sediment has moved out of that reach or out of that particular site or that particular watershed, and how much is in storage, and what the potential is for future delivery of sediment. And is the fish habitat actually being impacted by the road sediment? And if it is, then restoration would have be beneficial to reduce that impact. Or if it hasn't been impacted but is threatened, then protection measures, which would be in many cases similar to the restoration measures, either through road upgrading or decommissioning, to eliminate the threats that exist. The second type of monitoring is implementation monitoring. Once you prioritize your sites and actually develop an implementation plan and implemented the project, whether you're decommissioning a stream crossing or a road reach or excavating unstable fill material, determining whether the proposed restoration project was actually done as it was designed, or as field conditions dictated, it was appropriately revised in the field. Implementation monitoring is an important component to be able to document that what you said you do, you actually did, and that the original design was appropriate for the site. The next type of monitoring is effectiveness monitoring, and this gets a little more difficult because you have to determine whether it worked. So did the project effectively prevent short or long-term increases in sediment delivery, and did it perform as intended? So this implies some temporal aspect, whether it be a short-term period after the project was completed for a year or two, an intermediate term period for maybe 5 years, and then in the long term, was it effective? And really in the long term, because you're dealing with stochastic climatic events, you really have to determine whether it's gone through a stressing event, because most of the work that you do on road systems are stress-related. Their effectiveness is only measured by how it responds to major storms and events. So effectiveness monitoring is a key component of that 4 elements. And then finally, validation monitoring. And this is the most difficult and trickiest. Did the downstream fish habitat and channel morphology change as desired or as you expected them to? And have fish redistributed or utilized and responded positively to the work that was done upstream and upslope? We'll talk about some of the limitations of validation monitoring and some of the complications and difficulties in undertaking that part of the monitoring kind of scheme. The first 3 types of monitoring are much more easy to do at the site scale, and even the effectiveness monitoring is reasonably doable at the off-site scale too, but validation monitoring becomes another more difficult problem. So what is the problem with biologically based validation monitoring? Because when we're talking about, well, it could be water quality based too, which may be a little more amenable to monitoring, but biologically you're looking for improved fish habitat and improved water quality. And so really, bottom line is you want more fish, and can you actually generate that? So validation monitoring of especially road-related sediment projects is usually not carried all the way to fish population response, because there are so many other factors that control fish populations and distribution. And it's not just the restoration project that's limiting fish to a reach of stream or a sub-watershed, probably. It's a lot of other factors, including natural erosion rates and other sources of potential impact, including, offshore conditions and in-stream conditions outside the area where your project is occurring. Typically, what we use is habitat-based monitoring, maybe combined with fish production models that will illustrate the expected effects. And this is the way Oregon does it. Essentially, they say, look, our validation monitoring is going to be looking at fish habitat, and we're going to make the assumption, the logical scientific assumption, that if we build it, they'll come. So if we produce good habitat, then the fish will utilize that habitat. Rather than actually trying to monitor the fish, they're monitoring the habitat, which is a little more reasonable, a little more doable in terms of actual monitoring channel conditions and riparian conditions and habitat conditions, pool depths, things like that. But in practice, even habitat parameters are not very easy to monitor. And more importantly, they're not uniquely associated with your project. And it's usually the farther you get downstream from your particular project site, the more difficult it is to be able to identify changes that happen downstream with the impact or effectiveness of your particular project, because there's so many other variables. As you move downstream, it seems almost asymptotically increasing or exponentially increasing the amount of uncertainty there is that you could actually pin any changes you see in the habitat, in the stream channel condition and morphology to the project work you actually accomplished upslope or upstream. Well, and working with Redwood National Park and their watershed restoration program early on, when we developed our watershed restoration, which is mostly road decommissioning projects throughout Redwood Creek, it became real clear to us that politicians want to see monies allocated and spent on these expensive road restoration programs, and they want to see actual improvements in fish populations and reductions in endangered species listings. And they want to see species coming back. They want to see people being able to commercially fish. They want to see increased fish populations and diversity. And that's a tall order. Unfortunately, the politicians are, for the most part, the ones who fund these programs. And so somehow the connection needs to be made that while we can't give you that particular data, we can't uniquely say that what we're doing is resulting in increased fish populations, that there's enough scientific evidence, enough credible scientific logic to be able to tell you that what we are doing would end up at least beneficially affecting that, if not actually accomplishing it. So it works well in concept and in scientific kind of thought process, but there's actually little or no real data documenting fish population or habitat improvements resulting from sediment reduction projects. It takes a long time for those things to occur, and there's a lot of other factors that affect those. And looking at Walt Duffy, who in 2003 wrote, as of this writing, we could not find any validation monitoring programs that are assessing the biological responses to watershed restoration. And that was the case in 2003. And I think it's improving somewhat. I think the state of Washington and some other habitat conservation plan monitoring and things are trying to get at that, but it's a very difficult question and one that's fraught with a lot of uncertainty. Habitat and fish population improvements occur over relatively long periods, require heavy commitments to monitoring, and that's both logistical commitments and financial resources. And while the scientific logic has said, well, you need to turn off the sediment, the spigot of sediment, in order to improve downstream habitat and get your fish populations back, there's not a lot of research monitoring that has been committed to actually showing that that's the case. So here's some things that I took out of the literature. NIMS has said that monitoring and adaptive management essentially are essential ingredients for conservation plans under ESA. So politicians and NIMS, I guess, are saying that it's an incredibly important component. And monitoring is an essential element of the state of Washington's statewide strategy to recover salmon. And out of all the western states, I'd say Washington is probably farther along in the process of developing a decision management system for adaptive management based on what's happening in offsite and downstream areas, both biologically and habitat-wise. So that's a model that I think deserves probably some additional research and review of. Effective monitoring, and this is for the state of California by Drew Coe in 2009, basically said effective monitoring is necessary for the protection and restoration of aquatic resources and a critical step in refining management practices, not only the restoration management, but also like forest management or landscape land management, ranches, things like that. But he also said implementation of a statewide adaptive management program in California will be difficult. There's just not enough cooperation and communication and resources to be able to make something like that happen. So while almost everybody has identified that it would be critically important to do this type of monitoring, it's not essentially being done because of the difficulty and cost associated with doing it and the uncertainty associated with it. You're not sure you're actually going to get an answer or a correct answer. In Oregon, they conduct implementation and effective monitoring, but rarely employ validation monitoring, even at the habitat level. In California, we have a fisheries restoration grant program by the Department of Fish and Game, conduct both implementation monitoring on 100% of the projects, effectiveness monitoring, I believe, on like 10% of the projects, and there's minimal biological validation other than perhaps in fish passage projects where the validation monitoring is simply a presence-absence determination. In Washington, they're developing in their statewide strategy to recover salmon adaptive management that uses all three types of monitoring, and their long-term validation monitoring is restricted to what they consider high quality or important representative watersheds that cover a variety of different landscape areas. The federal government in their interior Columbia River Basin in-fish and pack fish programs decided that they couldn't make the jump directly to validation monitoring. So instead, the managers decided to focus their monitoring efforts directly on site-level restoration, especially for road-related sediment. And they use predictive tools, GIS modeling tools, to be able to determine whether the restoration they do is likely to have the effects that they're looking for. So it's more of a modeling kind of evaluation. And in the U.S. Forest Service, in the western states, have a legacy roads program, and it's mostly for decommissioning unneeded and problematic roads. They also employ this, what's called a GRATE model, as a predictive tool to evaluate treatment effectiveness. So they don't actually evaluate effectiveness. They put it in their model, which is a fairly sophisticated model based on a lot of site measurements, to be able to determine whether something's likely to be effective or not. And that's what they use as their monitoring of effectiveness. And this is a cover page for that geomorphic roads analysis and inventory package. It's basically a fairly complicated GIS modeling package that allows a lot of site data to go into it that will then, like connectivity and stream crossing, culvert sizing, and things like that. So it's a hazard assessment combined with an analysis as to whether the treatment of those hazards is likely to end up in the downstream results that you're looking for. So that GRATE model, they have 383,000 miles of road to look at, so obviously they can't be in the field determining effectiveness at even the watershed scale on a regular basis. So they use this modeling effort instead. So, and it's based on sediment production using empirical factors and sediment delivery based on distance to stream and drain point locations and observations, and landslide risk using something similar to ShallStab based on sign map DEM modeling, and gully risk based on contributing areas and hill slopes below drainage points on roads. So they use the model essentially to model the validation that the work they're doing is both prioritized and effective. Well, I'd like to get down to a little closer to where we can actually have some reasonableness, reasonable expectations that will be successful, and that's mostly at the site and reach level. And even the channel reach and habitat unit would be effective and could be done, but it just requires more effort, and there's more uncertainty associated with it. I feel more comfortable working at the site level, the road reach, and the road network level when we're talking about road upgrading and decommissioning projects. As you can see, these are in kind of descending order of size and spatial dimensions. Working at a landscape and river basin, you're going to result in higher costs and be able to generate broad and inferential linkages between what you're doing in the watersheds with what's happening in the rivers and streams. Whereas at the site level and the road reach and road network, and even at the channel reach level, your costs are going to be lower, you're going to get more detailed and definitive information, and the linkages will be a little easier to establish. The problem is most of your habitat is probably going to be off-site downstream, and being able to make that inference is going to be based on good scientific rationale and educated estimates. So in small basin monitoring, so we have small basin monitoring and we have kind of site monitoring. I want to talk about the two of those a little bit. In small basin monitoring, probably the most effective tool for doing that is called the Bakke study, before-after control impact. It allows pairwise comparisons, and you can do these either on small basins, or you can do them, for example, on individual features on a site. For example, on a decommissioned stream crossing, you might choose one side slope to treat, and the opposite side slope adjacent to it to not treat, to treat with a different kind of practice, whether it be mulching or windrowing or whatever it is, and then you can actually conduct an analysis as to what's most effective at that scale. If you're doing small watershed studies, you want the small watershed to be largely treated. So you want a lot of treatment in the watershed so you can pick up what's going on toward lower down in that particular watershed. And then you have to have control watershed too, in which those treatments are not applied. Requires the Bakke study design requires deferred treatments, so you're going to have untreated areas, and you might have to have those untreated areas for a number of years to determine whether your treatments are effective or more effective than not treating it. So if you're decommissioning a road, if you have to have some roads that are high priority that you don't decommission, and some roads that you do, so you can compare them over the long term until those stressing events happen and you get activity at one or both of those areas. This is problematic in the real world because most untreated areas that are high priority, landowners are anxious and agencies are anxious to get those treated. So setting up this kind of experimental setting requires a fair amount of discipline and agreement with the regulatory agencies that this has validity. You also have to have 1 or more decades of both access to the treatment sites and funding. And I put the and funding in red because typically it's not there. Even when you make proposals to agencies that fund these kinds of projects or that have regulatory authority over those resources, they're rarely interested in funding something that's going to last for 1 or more decades. They just don't have the ability to do that. They don't have the vision for funding out that far to be able to make that commitment, and it becomes difficult for them to do that. You have to have 1 or more decades because your sites, whether they be road upgrading or road decommissioning, you have to go through stressing events. Downstream areas take a fair amount of time for a response to occur, and validation is also fairly time-consuming in terms of the amount of time it takes for fish populations to distribute, disperse, and occupy those areas. So the kinds of things in small watershed response models or variables that you might measure might include stream discharge and water quantity, water quality, stream channel, geomorphology, cross-sectional area, longitudinal profiles, things like that, and channel habitat and macroinvertebrate in terms of biological response. I don't have fish on this because in most cases there's so much variability associated with that particular parameter that it's not possible to get good definitive answers. More commonly, we work at monitoring at the site scale, and we're looking at a conceptual model that assumes that what we do at the site scale will have beneficial effects in downstream areas. It's easy to make that assumption. It's hard to tell local politicians that we're making this assumption that what we're doing at the site scale is having benefits downstream when you don't actually have evidence of that. But we're in many cases left with that conundrum and have to follow that. When you put together site-scale monitoring, you have to have clear hypotheses about what your treatment outcomes. You have to have clear statements of objectives and clear hypotheses about what the treatment outcomes are going to be so that you have something to essentially evaluate or monitor. Those elements that you do monitor, those whether they be hill slopes or stream channels, excavated crossings, culvert installations, whatever they be, they have to be sensitive to changes that you expect. And they have to be able to, the measurements have to be repeatable so that anybody coming in can take those measurements and come up with the same numbers. And it has to be relatively cost effective. Interpretation of site-scale effectiveness monitoring should be fairly straightforward. If you get a void, if you get a gully going through a particular site you've done work on, or at the outlet of a culvert, or through a stream crossing, the monitoring results should show that fairly clearly, and you should be able to interpret the cause of those. Working at the site scale, there's a pretty short lag between treatment and response. For example, on road decommissioning, most of the adjustments occur in those decommissioned stream crossings in the first 2 years after they've been excavated. And then you might have a stressing event 5 or 10 years later, but the amount of adjustment that occurs in the stressing event we found is not as much as occurs in the first couple of years that site goes through normal winters. And the common site scale response variables you'd look at would be, for example, hydrologic connectivity, what it was before, what it is after, site scale erosion through a measurement of voids, stream channel geomorphology, cross-sections and profiles, fill slope stability, did it fail, did it not fail, if you're treating unstable fill slopes along a road. And then the only active kind of monitoring would be water quality, which would be mostly turbidity measurements above and below the project site, and then continuously or sporadically below the project site to see how suspended sediment changes over time as a result of your project work. The conceptual model put together in one of Richard's publications shows here for the problem identification, treatment, short-term adjustments, that's year 1 and year 2, with generating some water quality impacts and site channel impacts. Site stabilizes, year 3 through 5, intermediate term, reduced chronic erosion sediment delivery, improved response to stressing events, reduced long-term sediment delivery, especially with road decommissioning. We can almost assure that that's going to be the case, and we infer that that's going to be the case with our upgrading of streams, of roads, especially at stream crossings, and then improved habitat and improved water quality. And the inference then is that those result in increased salmona diversity and population in downstream areas. And that's an assumed, that's not a measured quantity, but that's an assumed logical scientific assumption based on the conceptual model. So let's take a look at some of the types of road stormproofing we deal with. We saw this before. We have both road upgrading and road decommissioning to evaluate in terms of sediment control coming from road systems. So the practical objectives we listed is reducing the failure potential, i.e. the frequency of failures, reducing the volume or magnitude of failures when they do occur, and reducing road-related sediment delivery. Those things should be fairly easy to measure, fairly straightforward to measure at the site scale. You just have to have the stressing events to be able to identify that that was actually the case. So if you have just normal winters after your road upgrading, for example, you're not going to have any results for failure magnitude, for example, or sediment delivery, where you have very few results. And then the other ones we looked at were lower water quality and aquatic impacts, lower costs of storm damage repair, fewer washout than road failures, less downstream turbidity, and these are all things that are amenable, at least in large part, to some type of site or immediately downstream from site monitoring techniques. All right, well, the three places on roads, whether you're dealing with upgrading or decommissioning, that you really evaluate through the monitoring process would be stream crossings, potential road-related landslides that would deliver to stream channels, and road surface runoff and related erosion, primarily through the process of hydrologic connectivity. These are the things we talked about last week. And so the goals for road upgrading are essentially to minimize erosion and sediment delivery, maintain hill slope stability, and reestablish natural drainage patterns. So through implementation monitoring, you should be able to determine whether your project work was accomplished according to designs, and then through effectiveness monitoring, whether that project work actually resulted in those elements. Through decommissioning, there's a similar kind of definition: minimizing erosion and sediment delivery, maintaining hill slope stability, and reestablishing natural drainage patterns. That's essentially a CAL FIRE, a slightly modified version of the CAL FIRE definition of road abandonment, which is another name for decommissioning in their context. So the technical standards, and these are the things that you want to, in implementation monitoring, make sure that you accomplished. For stream crossings, for road and landing fills, excavating and stabilizing them, and for road surface drainage, hydrologically disconnecting them. This doesn't have a lot of actual numerical values associated with it, so we get a little more specific when we're actually putting together a checklist for implementation monitoring to say, we did these things according to the standards that we said we'd do them at. And then for effectiveness monitoring, being able to monitor the important ones that it'll tell you. So what are some of those implementation monitoring parameters? Stream crossings designed for the 100-year flow, no diversion potential, that's zero diversion potential. Low plug potential, that's a subjective, essentially field verification as to what the plugging potential of a stream crossing culvert is, and you can usually come to a fairly good agreement as to whether it's going to be high, moderate, or low. Stream crossing outlets are protected from erosion, or they're not eroding. That's pretty straightforward to put on a checklist. Culvert inlet and outlet bottom are in sound condition. Again, a pretty good checklist item. Undersized culverts and deep fills have overflow pipes, so either they do or they don't, or there's a reason they don't that may not be evident that can go into the monitoring. Bridges have stable non-eroding abutments, don't restrict flood flows. That's pretty straightforward to put on a checklist. Unstable fill slopes are stabilized and removed. Well, that requires you to correctly identify the unstable or potentially unstable fill slopes, and then to have chosen and accomplished the correct stabilization or removal method. Road surface and ditches are largely disconnected. That's not a numerical thing, but we'll get into numerics a little bit with hydrologic connectivity. Again, we'd like to get it into the 10% range, 10 to 20% or less if we can for upgraded roads, and less than 5% of hydrologic connectivity in the decommissioned roads. And finally, the Class 1 stream crossings accommodate fish passage for all life stages. And you can get a pretty good handle on that looking at doing some actual fish monitoring above and below, both in juveniles and adults, to be able to determine whether you've got all life stages on both sides of your Class 1 stream crossing, whether it be upgraded or decommissioned. So for road fill slopes, it's pretty straightforward. Either unstable or potentially unstable fills that would deliver sediment to a stream are stabilized or excavated. So again, you have to identify it correctly, then you have to prescribe it, and then with a standard, and then treat it to that standard. And that either happened or it didn't happen. That's amenable to checklist verification. Spoil is placed where it won't get into a water course. That's fairly straightforward field determination. And excavated spoil is placed where it won't aggravate or cause a slope failure or landslide. And believe me, I've seen places where spoil is taken out of one place and put in a place that's even worse. So that usually can be evaluated in the field too. And then finally, for road surface drainage or the hydrologic connectivity, again, we like to get the connectivity to 10 to 20% or less. Ditches are drained frequently with rolling dips, ditch relief culverts so that there's no gulling at their outlets. Overflow from ditch relief culverts doesn't connect to stream channels, so it doesn't discharge into stream channels directly or indirectly. Gullies at ditch relief culverts are dewatered. And ditches do not discharge into active landslides or unstable areas. And decommissioned roads have permanent road surface drainage and don't rely on inside ditches. So these are all things that can be put in, and the Department of Fish and Game has put these kinds of things into one-page implementation checklists that their staff goes out to evaluate virtually all the road upgrading and decommissioning projects that are undertaken under the Department Restoration Grant Program. So for road decommissioning, I'm going to just quickly go through these because we talked about them last week. Excavating the side slopes to 2 to 1 or a stable angle. Making sure you've got a relatively straight line profile between the natural channel above and below the crossing. Exhuming the original stream bed, looking at a crossing width that will accommodate the 100-year flow, 100-year peak runoff event by looking upstream and downstream at what the natural channel tells you what that channel width ought to be. The approaches are disconnected. The road approaches and road reaches are disconnected, so there's less than 5% hydrologic connectivity on a decommissioned road. Fill slope landsides, again, with those with potential for sediment delivery are excavated and removed. And the post-treatment sediment delivery of excavated stream crossings is less than 5% and preferably less than 2% of their total potential erodible fill volume that you measured prior to conducting the project. So some of the things we looked at, stream crossing, stream culvert alignment. This is both showing vertically and horizontal alignment as a standard. 100-year stream crossing culvert inlet with any kind of appropriate inlet devices to either reorient flow, reorient organic debris, and critical dip installed over a hinge line to the crossing so that you don't get stream diversion if and when the culvert does plug. All these things should help reduce the likelihood of failure, i.e. the frequency of failure of stream crossings, as well as the magnitude of failure when they do fail. By putting in the critical dips or dipping the whole crossing, you're removing a fair amount of the volume of the crossing and lowering the amount of sediment that could potentially be eroded and delivered. Critical dips at culverted crossings, you can see the one we saw last week in top, making sure that they're properly installed according to the design standards, and then in the bottom one showing one in the Hopland Research Station that where a new culvert, 100-year culvert, was actually installed. It plugged in the first winter, unbelievably, or believably. The inlet plugged and the critical dip worked great. You can see where the water came over the fill and washed right back into the stream channel with very low consequent erosion. And that's what you want. In converting culverts to bridges, if you have fish passage issues, making sure that you have fish passage after the project, and then replacing culverts or undersized or under-designed bridges with appropriately designed bridges that are wide enough to allow the channel to flow underneath the road, underneath the bridge without any constriction or impediments to fish passage. Hydrologic disconnection, make sure your bridges and your stream crossing for the most part are as disconnected as possible. In this case, water flowing from the bridge away from the bridge, not into the stream. And in this case, armored fills where you've followed the design standards we talked about last week and the construction techniques so that your armored fill crossings do not erode during the design storm period runoff events. Unstable fills, The design standard is excavating the fill enough, a sufficient amount of the unstable fill at the on the road fill slope, so that anything that does fail won't be volumetrically significant or large enough to actually enter the stream channel, and disposing of that spoil in a safe manner. And then finally, the third element, treating hydrologic connectivity, where you have insloped roads with ruts and berms and gullies on them, and converting them so that the standard is the road is hydrologically disconnected and disperses runoff uniformly or intermittently along its length, so that you don't get gullies or any connectivity to adjacent stream channels. Again, this is an example of a road before that was insloped with a ditch, so all the road surface runoff and the turbidity coming from that went into the ditch and down into the stream channel. And then afterwards, you can see the road is now, you can't see it, but I'll take my word for it, the road is outsloped, has rolling dips, and the ditch simply takes clear flow from springs and seeps along the cut bank and discharges that into the stream. And again, your measures essentially are measuring connectivity. You know, what was it before treatment? What was it after treatment? And is there anything significantly more that you could do to reduce hydrologic connectivity? In this case, getting it down to 7.5% was, I think, great. And knowing that you could even probably get it down to below 5%, depending on whether you wanted to go that extra mile. Okay, monitoring road decommissioning treatments. Those are road upgrading, road decommissioning. The standard for ripping is like 3 to 4 passes, disaggregated to about an 18-inch depth at minimum, with continuous coverage over the road surface. Putting frequent crossroad drains in so that none of the drains carry significant runoff or enough to actually cause any gullying or significant sediment transport from the dips, and no sediment delivery. Outsloping, essentially dispersing runoff uniformly along an outslope reach so that you don't get fill failures along the outside edge, and you don't get significant erosion along the outside edge of your outsloped road that would enter a stream channel. Imported outsloping, using your roads as spoil disposal sites, which is another effective road decommissioning technique, just making sure there's no delivering gullies or fill slope failures that occur in the long term. This shows a 4-year period from project time to the time the third photo was taken, and you know, it's been another 7 years since then, and this is still entirely stable and completely revegetated with alders. For stream crossing decommissioning, the standards are side slopes that are 2 to 1 or less in gradient, or to the natural hill slope gradient, whichever is less, and the stable, the cross sections and profiles of the excavated exhumed stream channel are stable and non-eroding. For decommissioned Class 1 stream crossings, making sure you got fish passage above and below for all life stages, and that the side slopes and channel are stable and non-eroding, and not delivering excessive amounts of sediment, especially in the intermediate or long term. And finally, for unstable road and landing fill slope excavations, making sure that you've identified the potential fill slope failures along your project area, your project road reach, or your watershed, and that you conducted the excavations to remove enough of the material, maybe not all the unstable fill slope material, but enough so that if there was a failure of the remaining material, it wouldn't enter a stream. That's the bottom line for it. You want to make sure that we're not getting sediment delivery from the fill failures that have been identified. Measures of success for road decommissioning. Again, 95% of the predicted erosion and sediment delivery have been avoided or eliminated, so you only have allowance of maybe 5% of what you predicted was going to occur actually occurs, and we found that to be a reasonable expectation that you should be able to achieve. And in the long term, after stressing events, you should have a lower frequency and delivery from road fill failures. You should have identified most of them and treated them, and your connectivity is less than 5%. So the standards are pretty well spelled out, and you should be able to monitor those, and over time, determining whether each one of these 3 has been successful. Again, we found some problems with decommissioning. And anytime you're doing monitoring, you're going to want to monitor those sites that weren't correctly identified and treated also to determine their effectiveness or their response over time, so that you can apply those to adaptively improving the restoration practices or the road upgrading or decommissioning practices you're employing. So lastly, I want to go through an example case study that we did looking at the restoration grant program. We had a contract with the Department of Fish and Game. We looked at roads decommissioned between under the grant program between 1998 and 2003. So there's a fair number of years there, 5 years involved. And we looked at a variety of different parameters. You can see that in that period, or roughly that period, you can see what the distribution of funding was in the grant program. It's not quite so skewed so much toward road upgrades and removals, but it's still a significant and expensive component. So it's important that we be able to do it effectively, and we do it cost effectively for the grant program. And so that really spurred probably their desire to take a look at the techniques that have been employed so far. So our goals in this were to identify and document the techniques that were employed to measure post-treatment erosion at the stream crossings, because that's where most of the sediment is coming from on road decommissioning areas. Collect attribute data that would allow us to determine causes, essentially, for that. Determine whether or not the decommissioned stream crossings met current standards for fish and game projects. And evaluate the existing work and the current fish and game decommissioning protocol. In other words, should it be changed? Should there be recommendations for adaptive management in the way road decommissioning is being done across the landscape under the program? So this was the distribution of projects we looked at, 10 different study areas all the way from the Oregon border down to Marin County. And we looked at different geologic types, different topographic zones, and different vegetation areas, and did a kind of not a random sample, but a sample distributed according to a variety of different elements that made sure we had good representation of road decommissioning through land ownerships and vegetation and geologic types across the region. The decommissioning protocol essentially is the same we just talked about. Excavating. This is an approved fish and game protocol, and this is what we measured the projects against, whether they had actually accomplished that or not. So this is more of a retrospective type of monitoring study than an active monitoring study that's over time. The side slopes, where they're excavated back to 2-to-1 grade. The channel profile was the natural channel profile through the crossing with no abrupt grade changes at the bottom or top. That the channel width was designed for the 100-year flow, and we would be able to evaluate that in the field as to whether we think that the actual channel they constructed, that they exhumed, met that criteria, and that the road approaches were hydrologically disconnected. So those are the standards that we measured in this monitoring project. So the population between 1998 and 2004 is 152 miles decommissioned under the grant program, and 1,142 treated sites, including landslides or potential fill slope failures, not landslides really, but potential fill slope failures, stream crossings, and other road drainage sites. Our sample population, in which we looked at the techniques that were used and the effectiveness of the erosion prevention work, we looked at 51 miles, or 34% of the roads that had been treated, and 449 treated sites, or 39%, that included 275 of the excavated stream crossings, where we were convinced that that would probably be, if there was a problem, that was where it would most likely show up. So the erosional features include gulling through excavated stream crossings. You can see the one on the left, minor excavation, the one on the right. You can see the person for scale there, fairly significant under excavation of the fill and resulting down cutting that had occurred. Again, on the left, surface erosion we looked at, bare soil areas on side slopes on the crossing on the right, all these areas here, what kind of erosion control techniques were used on those side slopes, and then looking at large-scale erosion on some other areas, and you can see here the person for scale down at the bottom here. So this is no minor amount of surface erosion. This was on the Steinecker Road up in the Salmon River, and in decomposed granite, where surface erosion is a very significant component of post-decommissioning erosion. And we looked at channel widening, both at the small scale and large scale on excavated stream crossings. And then finally at any mass wasting on excavated channel side slopes that occurred once they were exhumed and the stream crossing fills were removed. Sometimes you have slope failures occurring on the side slopes. So we use measurement techniques that are here kind of depicted by Randy Klein and work he did in the sanctuary forest of the Upper Mattole, looking down at a map view of of a stream crossing with stream entering here, going through and leaving down here. He had GSs, which are grab sample suspended sampling. This wasn't a part of our study, but we did do photo point monitoring, photos before the project were looked at. Photos were retaken after the project, and we do that as a regular part of our monitoring efforts also. So photo point monitoring, we found over the years is perhaps one of the most effective and one of the most convincing arguments for road, specifically road decommissioning. People who fund these projects love to see wonderful photos of roads before and after, because you can have some great before and after photos, and you can really show visually the potential benefit of doing that kind of project work. And then finally, the other type of measurement technique was simple void measurement. And in this case, this is a, see if I can get that pointer back. Nope. The upper diagram shows a cross-section of a stream channel with the way it was originally excavated and the smooth upper profile, and then the way it's scoured afterwards, and just the techniques used for measuring the void or the volume of erosion that occurred at the crossing, similar to the volume of erosion that occurred on a side slope failure, and then a plan view in the lower diagram showing cross-sections and lengths of channel where the void measurements are taken. All these different techniques I'll describe in a couple of minutes are included in a handout that is available for you. So what are some of the results? So the things we were looking at, we wanted to know whether we were getting more erosion, what process was generating the most erosion, and what types of features were responsible for sediment delivery in the post-decommissioning period, the short-term and intermediate-term period of the first 5 years after a stream crossings and roads have been decommissioned. I think I'm still here.
You're here, Bill.
Okay. And we found that channel incision and surface erosion were the two dominant erosional processes in terms of the number of erosion features. Surface erosion was very important because we had a limited number of sites in decomposed granite, and that skewed the distribution. The total sediment delivery in the upper diagram by erosional feature type. Surface erosion was the most important component, again, skewed by the inclusion of the Steinecker Road decommissioning projects, the huge crossings, and in decomposed granite. And we take that out, and we see a little more distribution that is focused mostly on channel incision and slumping and sliding on the side slopes. The average post-treatment unit sediment delivery for the crossings, you can see, was anywhere from, for gulling, about 2 cubic yards per feature, to slumps or slides, which were about a little over 20 cubic yards per feature. But you see a pretty consistent, 5 or maybe 10 to 15 cubic yard per feature sediment delivery. The causes of erosion, so important. Once we documented the actual occurrence of erosion and assigned a variety of different attributes to it, we found that stream crossing in the upper diagram, stream crossing post-treatment unavoidable erosion, things that it wasn't the fault of anybody either in terms of design or implementation, but most of it was due to overland flow, specifically on steep side slopes to excavated stream crossings, and natural channel adjustments, the two that are the most important in this one. 200 features in the overland flow category and 150 in the natural adjustments. But the one that's more important in terms of adaptive management is the bottom diagram, the number of features exhibiting erosion by cause. And unexcavated fill, you can see, is 120 sites or features where that was a particular cause. And so that was, for excavated stream crossings, that was the most important component. There was fill that was left in the stream crossing excavations that wasn't completely removed. Just want to make sure I get... Okay, and when we look at the cause unexcavated fill, these are essentially the same diagram showing the volume in cubic yards assigned to those particular causes, and you can see in the bottom diagram here, the unexcavated fill assigned a total volume of about 2,500 cubic yards over all the sites that we looked at. Okay, in the bottom line, volume of sediment delivered, volume of delivered sediment by adherence to the protocols. So we had the Fish and Game protocols about how you were supposed to do this. And if they actually did all the things in the Fish and Game Protocol, their total sediment delivery was about 3,000 cubic yards over all the project sites we looked at. And if they didn't, it was over twice that. So meeting the protocols, we found, was a highly important component of the project. And this is the unit sediment delivery. So for excavated stream crossings, particularly 30 cubic yards per site if they met all the standards. And that's an acceptable range of adjustment, less than 5% of the excavated or potentially deliverable volume if they had not done the site at all, versus slightly over 40 cubic yards if they didn't follow all the protocols. So the conclusions, the most common erosion features we found associated with decommissioning were channel incision, surface erosion, and mass wasting on the side slopes to excavated stream crossings specifically. The most common causative factors were overland flow, natural bank adjustments, unexcavated fill, and undercutting by excavation. The most common operator and supervisor error was under excavation of fill. In other words, they didn't dig out all the material that they needed to exhume the original stream. And finally, not finally, but almost finally, our analysis, our kind of retrospective monitoring suggests that the Fish and Game protocols for decommissioning are effective and appropriate, but they're not always being followed. And when they're not followed, you have higher rates of post-treatment erosion and sediment delivery and probably downstream impacts. You're less effective. The average post-decommissioning adjustment for a stream crossing was 5% of its original volume, so it kind of met the target that we were looking for. And then finally, stream crossing decommissioning was found to be highly effective for a long-term solution, since we essentially prevented 95% of the potentially erodible fill from actually failing and being delivered during large storm events. A couple of the references that I want to point your attention to are shown here, and these were reports that were written under when Richard was at the UC Extension Center for Forestry. And one on the left, he prepared with a couple other authors on monitoring the effectiveness of road system upgrading and decommissioning at the watershed scale. So it's really kind of setting together a study plan for how you might look at the effectiveness of large-scale and small watersheds, but fairly complete road upgrading and decommissioning processes, and how you might measure the response in downstream areas. And the one that we prepared, which is monitoring the effectiveness of upland restoration, and it really goes through a variety of different temporal scales, short, intermediate, and long-term, and it completely, with photographs and methodologies and descriptions, goes through the techniques, and I didn't decide to do that on this presentation. There's really not enough time. Looking at void measurement and surface erosion monitoring using pins and caps and bridges and sediment traps and tag lines and cross-sections and profiles and turbidity and suspended sediment sampling, and displacement surveys for landslide movement and maintenance and event monitoring. So we really looked at a variety of different things. That's all really laid out in pretty, I won't say pretty good detail as to how those things are accomplished. Some of the other references that will be appropriate for this in terms of road upgrading, again, the designing water courses for the 100-year flood flows of wood. Those are appropriate techniques to be able to make sure your designs are appropriate. And then the diagram on the, or the publication on the right, the field measurement of soil erosion and runoff. And then the restoration manual, upslope erosion inventory and sediment control guidance. There is elements in there related to monitoring of the project work that you're accomplishing. And then there's a lot of stuff on the web about monitoring stream channels. This is probably one of the more classic ones put out by the EPA, monitoring guidelines to evaluate the effects of forestry activities. And that would include, I suppose, restoration processes on streams. So those are important references to include.